Berlin. How are we feeling? The speaker's ready. Are you? It's the last talk of the day. Come on, give me some noise. Awesome. Perfect. So, you're here to learn how to teach your model to spy or defend. I don't know. I think that's on David, right? So, before I ask you to welcome him, make sure you ask questions in the app so I can see them and ask him questions at the end of the talk. And yeah, with that, give it up for David.
Cool. Thank you, thank you. All right. I know it's the last talk. I really appreciate everyone being here. So yeah, we're going to talk about keystroke loggers, but we're going to talk about acoustic keystroke loggers. So this is taking sounds when you press your key on your keyboard, taking that sound and translating it to the letter that you're pressing. So my name is David. I'm an AI ML engineer. I work at NetApp Instacluster, so NetApp. I've been doing the AI thing for a while. I have a very interesting background. Have done Kubernetes, I've done virtualization, done storage, backup recovery solutions. But yeah, if you want to chat a little bit later about all of those things, feel free. I can hang out over here afterwards. Let's just jump right into it. So this is what we're going to talk about. We're going to talk about the moral duality of AI and ML. And it's kind of interesting, right? Because you can do really cool things and you can do really horrible things. And we kind of just need to acknowledge that. And then we're going to talk about literally how to build an acoustic keystroke logger. And we're going to talk about what the data preparation, the process pipeline looks for that. And we're going to then talk about the model architecture. And actually, I'm going to do all of this by demos. So I'm going to drive all of this by demos. We're going to talk about potential real-world attack vectors. And then probably more importantly, how to protect yourself, like privacy, security, and making sure you don't fall susceptible to this. And then hopefully you'll have some time for Q&A at the end. So yeah, let's talk about the moral duality of AI and ML. So we all can see, and we can all imagine, and we all hope that we apply all this stuff for doing really amazing things like curing disease. So here's like a NIH article saying, hey, we're using AI and machine learning to do protein folding and finding new cures and everything. So this is awesome. This is like what I hope we all aspire to do. Now, this is the dark side. So in the United States, this is very frightening. So we started employing digital price tags in our shopping, grocery store. So when you're shopping for groceries, depending on the time of day, the price will change. And they basically change the price to do maximum extraction on how much you're willing to pay for your groceries. And this is frightening. And it's really scary. And this is downright evil, in my opinion. But yeah, you just need to be aware that what you put in your cart might be different in price than what's actually in store. So just pay attention to the things that are happening around you. And understand that some of this stuff can be applied for really horrible things. So the talk is focused around a practical deep learning based acoustic side channel attack on keyboards. I did not invent this. This is actually the archive article that is a research paper on actually how to do it. And what I did was I implemented it, the techniques and everything, how to do inference. And then I also made some improvements on it. But kind of the idea is that, hey, we need to be aware of stuff like this, and not only be aware of it, but provide the code, because if we kind of keep this encapsulated to only a few people who know about it, there's no potential way to disrupt it. And so that's kind of the idea behind this talk. So let's talk about how do you actually go about building an acoustic keystroke logger. This sounds like a far-fetched topic, and it seems wild. But ML audio classification has been around for quite some time. And there's many applications for this, and many people have been doing this in production. And fundamentally what you do is you start with a sound. You record some audio. Typically that audio then gets converted into some friendly format. So this is doing linear 16, usually 44.1 kilohertz for the sampling rate. And now you have a sample representation of audio. Now what you do is you take that audio and you convert that into a spectrographic image, so a spectrogram. And that's what this cool little fancy top image is right here. You have time and you have frequency. And then think of the coloring as a heat map of like what frequency at what time and what the intensity of that frequency is, and you have all the acoustic signature related to that particular sound. Now, if you take a look at the bottom picture here, each cell represents a unique or a different sound. And you can see, like if you take these two cells right here, just looking at it visually, you can tell that those two sounds are pretty similar in nature. And in fact, you can probably argue that they're the same sound. In fact, they are. And you can see the cell right next to it is instinctively, like inherently very different. And so you can see that's a different sound. So the idea here is like capture the audio, turn it into a picture, and then build an audio classifier based on that image. And the basic examples you see, which I've linked to here, is like a cat versus a dog, so cat meowing, dog barking. And a more real-world practical scenario is like if you were to wanted to alert medical personnel about a potential shooting. I know I'm from the United States, and that sounds a lot weird, making that association. But we actually do have like gunshot recognition, so that in urban settings, so that it can actually pick up saying that there is gunfire and then alert authorities to that particular location. But it needs to be able to distinguish other background sounds that are not even close to that, but sound similar, so like a car backfiring, for example. Right, you want to be able to not alert authorities every time a car backfires or there's a firework. So I live in Long Beach, California, and I swear every day someone is lighting off a firework, even when it's not 4th of July, and it's inherently very annoying. But that could be another example of like misclassifying that sound. So if you wanted to build something, right, we kind of have the basic principle behind it. So we're going to start with a data set, and we're actually going to reuse two existing data sets that I found on the internet. The first one is keystroke noiseless final. So this is a single keyboard data set where basically and it was used in a hackathon in Singapore in 2024. And it's basically a single keyboard where someone has hit A, record, A, record, A, record, gotten many samples for every letter on the keyboard. Then the second data set we're going to use is this multi-keyboard acoustic data set. And the idea here is we have now multiple keyboards, 6 of them, where they've recorded every letter and got a sampling for every letter for every keyboard. And so these are the two data sets that we're going to work with when we build our acoustic keystroke logger. So here's a little bit about the data processing pipeline. So, right, take the recordings, WAV files, linear 16, convert all of them to images. Then we're going to, since they're probably, and they are, in like a folder called A, folder called B, C, 0, 1, 2, 3, 4. So there's 38 different letters that we're going to categorize. So A through Z, 0 through 9, space, and enter. And we're going to create these spectrographic images. We're going to apply machine learning so that they can understand the subtle nuances within the pictures. We're going to use 3 different channels to track, so RGB, right? So red, green, blue, because this is a color image. And then we're literally going to use this image, all these images, to build this machine learning classification model. In the interest of time, I'm going to skip this because my head hurts. I'm sure everyone's got a ton of knowledge from all this stuff that's happening today. If you want to talk about the architecture in a lot more detail, you can meet me afterwards, but I've included it here for the slides here. So let's get to the first problem, right? We have a data set which contains sounds from one keyboard. And in any machine learning problem, you need to divide that data set into training data. So this is the knowledge that the model knows and learns. You need some portion of that data set in order to do validation. So this is, hey, as I'm doing the training, I need something to match that against, to say, hey, am I getting close to the predicting like what this letter is or this number? And then we need some portion for test, right? So we have some data set aside so that we can run all of our test data to see how well we did, right? This is kind of like the final exam. And typically, when you do any machine learning model, when you're training one, you have like 80% training data, 10% validation, and 10% test data. And that's what we've done here. So instead of talking about it a whole lot, let's actually just take a look at everything here. So I'm going to start with the data processing pipeline. So I have a folder called data. You can see the test, training, validation. I'm just going to pick training. I've pared it down. Otherwise, this would take a ton of time. So we have the the training data for the letter A. And then if we look in here, you can see a number of WAV files. Now, we're going to run a script, which then takes each of those WAV files and converts them to an image. So let's go ahead and do that. And notice we don't have an images folder, and I can never remember the command, so I have a little cheat right here that I can copy and paste it. All right. So if we take a look at, now we have an images folder, and if we go ls images, you can see we have the same training, test, validation, the letter A, and now we have a bunch of PNG files, images. So let's actually open up one of these and take a look. So this is an acoustic spectrographic image for the letter A. Now we need to take all of this and now build a machine learning model to take all of these images, which we can actually see right here. I'll pick training, and you can see all the letters. And if I just pick any letter at random, the letter I, those are the images for training for the letter I. And so we're just going to build our machine learning model to be able to classify those letters. And again, remember the pictures represent sounds, right? So the way you would do that is you go python1_train, and we're not going to do that because that requires far too much time. It requires about 14 hours. But we are going to run inference, and we're going to use the letter S, which you can see right here. And we're going to run that through our pre-trained model, and we're going to see what we get as a result. And as you can see, single keyboard, the letter S, this is instance 9, right? Because there are many instances. We can actually predict this with 100% confidence using a single keyboard. Now that's pretty amazing, pretty frightening. So that's a single keyboard. So then, and I actually did the single keyboard, and I said, man, maybe we'll get close enough. I didn't even think about coming to the multi-keyboard, and then when I realized it was 100%, I was like, holy crap, like, let's try multiple keyboards. And so here we have multiple keyboards. So we have a Lenovo, we have Apple, HP, MSI, and we have, I forgot which keyboard it is, it might be the Lenovo, over Zoom. Someone is hitting the letter and recording on the other side of a Zoom call and like capturing that sound. And then we also have it for Messenger. And so this is the multi-keyboard acoustic data set that we're going to use for this next section, for this multi-keyboard detection. Just like before, we need to have representation in every group for training data, validation data, and test data. So we need to split it up equally, right? Equally as in the same equal parts. 80%, 10%, 10%. Train the machine learning model and have the ability to use some training data to test. So let's go ahead and just demo that. So just like before, clear this to make it a little easier. And I've provided So right here, this is the actual model right there. So because it actually takes like an H100, it takes about 14 hours to train the model, and it's a non-trivial amount of money. So I've basically built a model that you can download yourself, that's in safe tensor format, that you can play around with on your own machine. But if you were wanting to build this on your own using the data set, you would go python1_train. That would take, again, 12, 14 hours. But let's just run inference. And we're going to pick we're going to pick the Lenovo keyboard, the letter H, which is the first letter, and then this is like instance for the sound, or instance 5. And we're going to run that through our trained model, and we're going to see what we get. So you can see that we get, this is the most confident score. So the letter H, it's correct. And then you see the confidence score drop off massively, right? 48%. And then its second guess is G, 24%. The letter J, 16%. And why I decided to print out 5 is important, which we'll talk about in a little bit here. But it's actually still able to do it, just with a much lower confidence level. So, now that we can kind of do this for multiple keyboards, I thought it would be an interesting exercise to now take the images, right, which represent WAV files, and string them together and do inference on each one. And the idea is to simulate me typing on a keyboard. And the message that we're going to spell out is, where is it? I think probably all the way at the end. Oh, is it this wrong off? Hang on one sec. Oh, I'm totally in the wrong folder. It would be helpful to be in the right folder, right? Oh. So the message we're going to spell out is hello people. So HELLO spacebar PEOPLE. And I picked the Lenovo keyboard just because I just picked one at random. So let's go ahead and take all of these images, right? This is kind of like me simulating me typing on a keyboard, spelling out hello people in a Word document. Now, you notice right away, so we have the original, right, what we entered in, hello people, right, the first letter there. And then I picked top k equals 2, which is give me your top 2 most confident guesses. And this column is the first most confident one, right? So we can see HELLO space OEOOLE, which is definitely not people. But kind of one of the improvements that I realized on that research paper was that maybe the most confident score doesn't, maybe need to look beyond that. And so if you actually look at the second most confident guess, you have PEOPLE. So you have the information and it's there. Now, we just need to be able to use every possible combination in order to figure out what the original message is. Now, the problem is that we actually have, what is this, 12 characters in this tiny little message. 2 to the 12th power is far too many combinations to try to guess. And that would take far too long. And kind of the idea was here was, hey, I'm going to take the combinations and put them through a spell check, super simple, and be able to say, hey, you know, let's spell each word out. But doing 2 to the 12th number of combinations is far too, it would just, it would take years, right? So I had realized that there is one key on the keyboard that is vastly different than every other key on your keyboard. Anyone want to take a guess what key that is? Spacebar, absolutely. It's a unique key because of its shape. It'll have a unique sound. I can use that to delimit the message. Whoa, chop it up. And now I have two words. The first word is 2 to the 5th power, which is 32 combinations. The second word is 2 to the 6th power, 64 combinations. And now this problem is far more doable. And so we're actually going to do that. And we're going to see if the internet's going to cooperate here. We're actually going to do this live. I'm going to hit an API service that does spell check. We're going to take the limit using the space key, run the possible combinations, do the spell check, and we're going to print out in the console every time I hit a correctly spelled word, and we're going to go ahead and see what that looks like. So right away, you can see we have one word found, right? This is the first word because we're delimiting by the space key, 5 letters, 32 different combinations. We're also going to print out something which is very interesting, is just in case it becomes difficult to figure out what the word is, we're going to print out the probabilities for like the words and like what we think that particular chain of letters, what the probability of that being a word is. And so we're also going to collect that as well. Because the idea here is that if you have to have like a person validate this, if you were to type out a multi-paragraph Word document, that would take forever for a human to validate. So the idea here is to do this in a completely automated fashion. And we're going to see how long this takes. Oh, there we go. Excellent. So we'll just take a look at the first word in the interest of time. So hello, which is the correct word. Most probable, 0 is correct. I know it's weird. But you can see different combinations. So H-E-L-L, bad word. Hello, which is the good one. Help, and so on and so forth. Some other horrible words that don't make any sense. An optimization, we know we used 5 keystrokes. We can drop letters or words that are not 5 letters in length, right? So we can drop the first one, for example, right? Because we know it's 5 keys. And you can see we've already got a complete word for the second one, people. And if we go ahead and we look at our message, oops, where did I put it? Right? So we can actually do it. Now, what I also realized that every once in a while, I'm not going to be correct. It's going to give me a word that's not being able to be, detected correctly. And in that particular case, I kind of went the AI path. Like, how about if we built a specialized AI model where we leave a gap in the middle of a sentence and then use AI to predict what should be in that sentence, like in the middle of that position. So if we take a look at a couple test sentences we're going to run through. Where is it? It's always somewhere around here. Oh, here we go. First one, and I'll just run it. Berlin is the capital of, we all know that answer, right? So let's just go ahead and run that. And I provided a second sentence. So Berlin is the capital of blank, and we're going to use that AI model to give us a scoring of what the most probable word is, Germany. Small language models are distilled from large blank models. Most probable word is language, which is correct. So results. Single keyboard, 100% accuracy. Multiple keyboards, 46% accurate. Now, in normal machine learning world, 46% is horrible. That's a coin flip. But if you think about the probability distribution of just randomly guessing, 1 out of 38 is 3%, which is 46% is way better. And if I consider the second and third most probable guess, now it's a solvable problem. So this is the part where it's probably going to be very comforting. So these are keyboards we have collected sounds for. What this does not work for is keystroke independent data. So if I were to take all of the Apple keyboard sounds and use that to run through for inference, this does not work at all. So another way to say it is, if you take this machine learning model that I've created and you try to guess what the key press is on a keyboard it has not seen before, it will not work. It'll probably be that 3% accuracy, and it's probably garbage, right? You might as well just randomly smash keys on your keyboard because it's not going to work at all. But what I had thought about was, and this is definitely language dependent, let's say that if we have two keyboards that were manufactured in the same facility, in the same lot, so roughly around the same time, and you built your machine learning model around just that one keyboard, and you introduce that a new keyboard, the same make and model, manufactured at the same facility in the same lot, my conjecture is that this would probably work. And the reason why is because here is basically a representation of all of the different keys with the frequency at which you normally type. Now, this is English, and it's obviously different for every language. But in the English language, you type E the most, then T, then A, then O, right? Mostly vowels skewed to the front, makes a lot of sense. The wear and tear on your key as you're typing away is probably the predictor of like what sound that uniquely is going to make. And because the manufacturing similarity is so close, this might actually work. I did not test it because I didn't have a data set. Just kind of throwing it out there. So let's talk about real-world attack vectors. So this isn't a new thing. So back in the 70s, our phone systems used to be dial tone based. And here you had the kids cereal, which gives away toys. This toy actually, when you blew the whistle into a payphone, would give you free calls. It actually just resonates at the frequency at which you get free phone calls. So this was a legit thing. And if you knew about it, well, you probably were getting away with free phone calls for 25 years. But what had occurred to me was like, hey, if we were trying to take a single keyboard and apply this type of attack to one keyboard, one really well-known keyboard, what kind of keyboard would you try to attack? This was the first thought that I had. Right? And who knows what a credit card skimmer is? You would put it over the credit card skimmer, embed a microphone in there. When they slide their card through, that triggers the microphone to start recording the sound. Now you have the ability to try to figure out what that pin is, tied together. So how do you protect yourself against all this craziness? So do all of the things. Two-factor authentication, right? If someone's trying to listen in, typing away and stuff, you need some physical security in order to make this so that this is not a thing. Use passwords you don't know, right? Don't use passwords that you know that can be socially engineered out of you, like your birth year, your kids' names, your favorite sport, your pets' names. Don't use those things because now you can start to limit the scope of how you can guess a password. Different password for every platform. One compromised password doesn't compromise everything. Change your password frequently. I know everyone hates to do this thing from corporate land every 90 days, but there's a reason for it, and this is kind of the reason. And be intentionally difficult, right? If you ever seen in spy movies, right, where you're trying to tell someone a secret, three-letter government agencies trying to tell someone else a secret, what do? Turn on the shower, faucet, radio, because that adds interference patterns, right? And so be intentionally difficult. So everything you saw here, including the code, is in that GitHub right there. And This is actually a 30-minute talk. If you are interested in a 50-minute version, which goes into a little more detail, I've included a link there. I also talked about like the human aspects in a podcast that was recorded, and I've included the research paper. And the last link, I think this was just interesting. I spoke at WeAreDevelopers here last year, and I gave a presentation on how to confuse and trick AI in order to get them to do the things they're not supposed to do, to trick them to maybe use against a chatbot that you can maybe trick to get discount codes from your favorite retailer, just throwing it out there. You might want to check that one out. With that, if you found this workshop, or this, not workshop, I reused the slide, anywho, but if you like this session, go ahead. I believe that QR code is different. It is. But go ahead and rate it. Other than that, thank you. Hope you enjoyed it.
Awesome. Thank you so much, David. I've got a key for you that you cannot hack. It's a tiny mechanical key as a keychain.
Not that I want to frighten you, but one of my side things that I just like to do to learn, because I like learning stuff, is I know how to pick locks.
Oh. So I shouldn't show my keys on camera, I'm sorry.
It's actually pretty simple.
Fair
6
enough.
pins, 5 lengths, yeah. Anywho.
But yeah, super educational regardless. Thank you so much, David. Big round of applause for David. And a big round of applause for yourself, because this was the last talk of the day for stage 1. I thank you so much, and also the sound team and all the organizers and volunteers. Yes, thank you so much.